right. So does any of you have any questions? Everything's good?
Hello,
Let's
Professor. Good morning. I have a question.
absolutely.
Regarding the problems done in class on Thursday, are the ones in the final gonna be similar to those?
All right. So it's not supposed to be similar. Like I can say what
Like
questions
the same concept, not the same problem.
as I told you guys before, like it's the very thing that you have to review is the lecture notes. That's the most important part. You guys have seen the midterms, how it's I'm not sure if you try to locate the questions that was in the midterm in the lecture notes and how did you see it. Maybe it's the similar concept but in different shape. Maybe it's the same problem but different numbers. Maybe I add something, I put something. So as I told you guys before in the classroom, that the first thing that I look at when I put the exam is the lecture notes, because this is the main content that you guys are familiar with. So that's the very thing. But this doesn't mean that all the questions are going to come from the lecture notes. There definitely will be maybe one or two questions that either from the homeworks, either from the one questions, so that you can work your mind with new problems. You know what I mean? So my suggestion, right now there is only 2 days in the exam. I'm not sure how was your revision look like. So the very thing that you have to do um, is that you revise the lecture notes. I'm not sure if there's time to solve problems, but maybe you look at the problems, understand the idea. This is the most important thing, is to understand how to solve the problem, not memorizing the problem, not memorizing the number. This is not gonna work. So my idea is to have the equation sheet with you. You understand what every equation can do, and then on the other side, look at the lecture notes. That's, I believe, in the last day before the exam, after you finalize solving the problem, because you will not be able to solve the exam, I mean, like for final exams, until you have hands-on solving problems. Like you have to have your, I don't know, that's what I do when I have exams. I get like a bunch of white papers or whatever, engineering papers, and I have my pen and I have the problem, and I work with solved problems, like problems that I know solutions for. I put the problem in front of me without looking at the solution, try to think about it, if I'm able to solve it or not, and then I start solving the problem. Once I stuck, I look at the solution, and then I understand what I stuck with. So, all right, so we have background noise. Okay. Yeah, so that's what I'm saying is you have to not only looking at the problems and understand the idea, but you have to have hands-on solving problems. You have to have your pen, your papers, and then start solving real problem. Maybe we have 8 chapters. We cover the 8 chapters. So maybe you just look at the 8 chapters, go through them, solve one problem for each chapter. Like we have Tuesday and Wednesday. Maybe Tuesday you have one problem for each chapter, to whatever chapter that maybe you are done with 5 chapters, so that you keep your mind working, not forgetting what you reviewed. I like, for example, let's say an example, I reviewed chapter 12, 13, 14, and 15. So to make sure that I didn't lose any knowledge or any like any of these chapters, to keep track of what I did, you solve one problem per chapter today and tomorrow. So that's how you keep memorizing, solving the problems. Maybe you solve the examples that I have in my lecture notes. Maybe you solve things that it's already in the textbook. Maybe you look at the homework problems, so that you can understand the ideas of the problem and you can know how to start solving a problem. Okay, so I believe when you have the exam, the first thing that you need to think about it, what chapter this problem belongs to. Is it like impulse and momentum? Is it like chapter 12, the kinematics? Is it Newtonian? So based on what is given in the problem, that's how you will understand what this problem belongs to. Like, let me just explain what I mean by that. So for this actually was from previous revision. Like, like for example, if in the problem you are given something, a body that is moving from here to here, and I start to giving you this body cut this distance s equal to 6 meter in time 5 second, find the velocity, find the acceleration, find all these, that means that's a chapter 12. It's kinematics. It might be given in different ways. I might give you the velocity who started with, and I don't give the distance, and I told you that it stopped here. So I'm just playing with different problems, but it's the same concept. Look at the equation sheet. You will find the general rules. You will find the one with constant acceleration, non-constant acceleration. You have to distinguish between these. And it just like you need to understand the problem, understand the givens, and substitute in the equations. In a problem that is given, for example, I'm telling you a body that is, for example, on a slope and something like this, and there is this body is friction with mu k is equal to something, and the weight of this body has a mass of 10 kilograms, so you have to convert it to weight, and it's attached, for example, to a spring or a force that is pulling this body. So once we start talking springs, forces, and I give you weights, that means that right now we have to use either Newtonian kinetics. So I have to draw a free body diagram, and I have to do kinetic diagram and substitute with the sum of the forces equal to ma. This can be, for example, can be linear. So you will talk about x and y. It can be tangent and normal. So we will have to figure out the tangent and normal components. It can be r and theta, which is polar. That means the body is moving in a circle. So you will have to get some fx, some fy, or some tangent and normal, r and theta, and you have all the rules for these. Like you have, for example, what is Vn, how to calculate the V normal, or how to calculate E normal, which is V square over rho. So you have to understand the problem, what is given in the problem. Sometimes problems can be solved with a chapter 14, the Newtonian kinetics, and also can be solved with the work and energy in a chapter 15. It's kind of the same thing. So once, if we are solving a problem like this at a specific instant, like this instant, so that means I can apply the Newton's second law. So Newton's second law is applied at a specific instant, not over time. But work and energy. So we are talking about bodies start at a specific position and end at the final position. So that's when I give you a specific position, like position 1 and position 2. So that means that, and then I give you, for example, the distance S that this body did, and I give you a force that this body did. So that means I have force over distance. So that's mean that I need to use the work and energy. Maybe I use the conservative work and energy problem. So you will have to understand which one should I use. Sometimes problems, I give you two positions, but I ask you to calculate something at one instant. And I give you the other position just to calculate maybe the velocity here, to calculate the acceleration of the body here, so you don't have to use the work and energy and just apply the Newton second law at this position. Like the one that I give in the first midterm. Like I give you a curved circle like this, and I give you a body moving here, and it came here, but I don't want anything from this position. All what I wanted this position. I told in this position, you draw a free body diagram. You know, the weight is going down, the normal force is going up. This is the free body diagram, and the kinetic diagram. You will have the En acceleration this way, the A tangent this way, and then you sum the forces in the tangent direction and sum the forces in the normal direction. Depends if there's a friction here or something. So you have, my advice, any problem you will have to draw. You will have to draw something. That's what I do in any engineering problem. You will have to draw something. Most of the problems that we have in dynamics requires you to draw free body diagram and kinetic diagram because bodies are moving. So you will have, for example, a body that moving on a slope, something like this. You will have to put all the forces in the free body diagram. For example, this body has an external force P is pulling this way. If it has a spring like this way, you will have to put the forces in the spring Fs. You will have to put if there is a friction. So if this is the free body diagram, this is the kinetic diagram. If there is a friction, so, and I assume that this body is going up. So this is MAX and this is MAY. So if the body is moving up, and this is my assumption, I have to assume the F of friction is going this way, and I have to assume the normal is going up. I put all the forces in the free body diagram and all the movement, the acceleration, AX and AY in the kinetic diagram. And then all what I have to do, sum of the forces in the X direction is equal to MAX, sum of the forces in the Y direction equal to MAY. So I have bunch of forces in the X direction. I have F of friction. I have component. This force is NY. I have the component of the weight is going in the negative AX. I have the component of FS. I have the B, the external force, all this in X. I have some forces in Y. I have the normal. I have a weight component. I have a spring component. So you have to analyze all these forces and put them here. So yeah, Newton second law is applied at the specific instant, either at the initial position or at the final position. However, work and energy, it works between also two different positions. Like this one, it's only one position. I can apply Newton's second law at this position or at this position or at both of them. But when I tell you a body started moving, like start moving from this position and moved on a curve and came to this position. So right now I give you some information either to get the velocity V2 and V1, and I give you the information about the height here and the height here, H2 and H1, and there's a force applying on this body. So I have to know like the path of this force. So I have to know the S on this curve. So right now you need to apply that the T1 is equal to the energy at position 1 is equal to the energy at position 2. And the energy means that the kinetic energy T1 plus V1 plus the work done by the external force from 1 to 2 is equal to T2 plus V2. So that's right now you have two positions. Right now I need to deal with these two positions. I need to know all the information about this position. So if I said that this is the datum, so this is H2 and this H1. So H1 is equal to 0. So definitely V1, the potential energy is equal to 0, unless there's a spring. So I'm gonna add the potential energy that comes from the spring. So this is have H2, so I have to do the potential energy. If V1 has a value, and I'm telling that I shoot, like for example, a soccer ball, and the soccer ball went on a curve like this until it stopped here. So V2 is equal to 0. That means that the kinetic energy half mv2 squared is equal to 0. So you have to write all the rules because you will get points on the rules that you write. So you have to, like, if it's a problem that I'm asking, something that you use the conservation of energy, you have to write this rule and then expand this rule, how I can expand it. So you know that the kinetic energy is half mv1 squared. I know that the potential energy has two components. One come from a spring, one come from the weight. So the weight is mgh1 and the spring is half ks1 squared plus the work coming from 1 and 2. And this is equal to half mv2 squared plus mgh2 plus half ks2 squared. So I expanded this rule. Try next time is to substitute. So if you have V1, so you substitute with V1 here. If H1 is 0, so and 0 depends on when you decide where's the datum. I decide the datum here. If you decide the datum up there, so this is gonna be your datum, and any distance below the datum is gonna be negative. Any distance above the datum is gonna be positive. So yeah, so I have MGH1 if there is no spring, so these two are gonna be 0. I have H2 if V2 is equal to 0 because I said that the body's gonna stop here. So right now we need to understand the problem, understand like if I'm saying that the body, like the soccer ball were kicked until it stopped and after a specific time, so it means that at the final position, the V2 was equal to 0. I'm not gonna tell you it was equal to 0, but you will have to understand that means it was equal to 0. All right, just 1 second, guys, okay? I have a phone call, just 1 second. All right, I'm back. So yeah, I was saying that you will have to show all the steps that you are doing. You have to understand the problem. And also sometimes it gets confusing when it comes to impulse and momentum. But for impulse and momentum, you will have to review this chapter and see how's the wording of these problems look like. It is usually that you are given velocities. So you are given velocities and then because the impulse and momentum equation, it's mv, so you have m1 v1 plus the integration of the force dt is equal to m2 v2. This is how the impulse and momentum equation. So you will be given time and given velocities. Once you given time and velocities, or you are given something that can give you the time. So once you are giving these two components, like these time and velocity, that means this is an impulse and momentum problem. So that doesn't mean that this problem cannot be solved with work and energy. It can be, but with impulse and momentum is going to be much easier because you already have the time and you have the velocity. Here in this equation, there is no time. It's always distance and velocities. It's you are gonna give a geometry, and from the geometry you are gonna get the distance, and based on the distance and the velocity, you are gonna use the conservation of energy. So that's why you need to pick the best approach to solve the problem. Maybe use impulse and momentum in a problem that is needed work and energy to be used, or the optimal way to do it is to use work and energy. You are can do it, but it might be much harder, more steps. You need to convert the time and velocity to get distances. And once you get distance, you substitute in the, so you are doing extra steps to get to the answer. And we don't need that because each problem is going to have like 20 to 25 minutes to solve. And you need to allocate your time in an efficient way so that you can tackle all the problems. So I believe that's my best strategy. Like to solve an exam, you need to read the problem very well, identify what chapters that belong to, or what, not chapter, I mean like what approach that you are going to use. And based on the approach, you start to look at the equation sheet, see what equations that you have and how can you use them to solve the problems. Um, Yep. So does any of you have any questions so far? Is this any helpful?
I think that's, sorry, Professor.
Yeah.
I think that someone in the chat asked if there's gonna be like a pulley question. I guess
It's
that
gonna be
has
what?
to be, if there's gonna be a pulley question, I guess that's referred with a rigid body motion or something similar.
Well, it can be like it's part of the you already got a quiz on this. You didn't got any questions in them. You have to understand actually bully questions is easy, is not that difficult. It's just a bunch of lenses that you have to calculate them. So you need to understand how this system works. So uh yeah, so I believe
Professor, I have a question. Do you have an example for the rigid body motion of the related motion that we can see? Because that's like the one that I feel it makes sometimes it makes me confused, not with the omega, but like when the omega has to do with the with a fixed with the
yeah, I got you. I got you.
so basically like when the velocity has to go to one way or another one to
Okay.
just get the right K, the right I and stuff like that.
Yeah, so for let me look here something. Forget my folder. Let me actually check if I can have something that I can copy and paste it here. Maybe a question from the homework. Mm. I uploaded the model answer of the last homework if you guys want to check it. We had some problems with the naming of the homeworks files because there was some confusion about the fluid dynamics, how many homeworks were there. So just heads up. Mm. Screen. Right, so let's pick this problem. All right. Okay, so let's see this problem. Okay, so it says that you have this system, the velocity of the slider block C has 4 feet per second and it's going up. So it shows you the direction of VC. And here you wanna you wanna distinguish between the absolute velocity and the relative velocity. So the absolute velocity, if you have, for example, let's write this here. If you have, for example, a bar like this, and this bar is here, attach it to something here. So the absolute velocity is, this is the origin, O, and if this bar has omega this way, so this is, let's say OA, this is VA, and this VA with respect to a fixed location O, because O doesn't move. Like if we said that VA is gonna be equal to VO plus VA with respect to O. So VA is equal to VA with respect to O. Why? Because VO is equal to 0. O is not moving. So that's not relative velocity. That's called absolute velocity because the VA with respect to VA with respect to O is the same velocity as VA. Okay. But this is not the case if you have this something like this, and then you have your bar something like this, and this bar is attached to something like this. Okay, so this is fixed, and this is fixed. And let's say that this is A, B, C, D. Let's see what is absolute and what is relative. Okay, VD is equal to 0 because this is fixed axis and VA is equal to 0. If we want to get the absolute velocity of V, and I'm saying that this is moving with omega in this direction, by the way, you have to understand if when omega is negative and when omega is positive. Omega is positive if it's counterclockwise and the finger, the thumb is towards me. But it's negative if it's inside your paper or inside your screen. So that's negative if it's clockwise. So I have clockwise omega, which is negative, which is gonna give me a VB in this direction. So this is VB, and this is absolute velocity. Same thing with VC. If this is moving this way, this is gonna be moving this way. I have VC is going down. That's also absolute velocity. Both VB and VC are absolute velocities. Why? Because they are with respect to D, which D is not a moving point, has a velocity equal to 0. So this part is going to be equal to 0. So the absolute velocity is going to be equal to the relative velocity. However, I have B and C, the bar PC is in general translation or general plane motion, is not fixed axis rotation. It can have it can have a relative velocity. Like if I want to find out the relative velocity of P with respect to C, so I have to make C is gonna be my pace, and I have to find the arm between B and C. So that's what we call RB with respect to C. And if I want to find the velocity, knowing that the omega of this body is moving this way, so this is omega BC, because if this 3-bar linkages is moving and AB is moving this way, so the whole body is moving down. So let's see. This is gonna be, yeah, so C is gonna go down and B is gonna go up. So yeah, that's the omega B C. All right, so this is gonna be the direction of VB with respect to C. That's how this direction is gonna look like, and this is the vector. If we want to find out like V, for example, VB vector, VB vector is gonna equal to VC vector plus VB with respect to C. If you already, like, for example, I might give you in this problem, I might give you this distance, this R, and I give you this omega. If you know this R and this omega, you can get the absolute velocity VC by multiply R by omega. This is how we get the omega. Like if you have a bar like this here, and I give you the omega of this bar, and I want this velocity. To get this velocity, you multiply the R by omega. If you wanted the velocity here, you multiply this R by omega. If you want to here, so the velocity keep decreasing until you come here, and this is the point of zero velocity, which is the instantaneous center of zero velocity. So if I want to get VC, I get it from the omega here and R here. So I know this. Then I want to find what is VBC. VBC is going to be equal to the omega. Which one comes first? I believe if you look at the equation sheet, it's gonna be the R BC cross product omega BC. Is that right? Does any of you have the equation sheet? So everything you'll find it here in the, I think I have it published. Yeah, by the way, you have to print the equation sheet with you. I'm not gonna print it. Maybe I will have 4 or 5 just in case if somebody forget, but you will have to have the equation sheet with you. All right, so let's see what we have here. If we go down, I believe I have it many ways. Okay, I have actually omega before R. So, and this is gonna be a huge difference because it's gonna give you a negative. So I have to have omega multiplied by the R vector verse. So let's swap these. So you will have omega BC crossed by R BC. How can I get RBC? You definitely are gonna getting a distance like this and distance like this. So you get RBC as I and J, and omega somehow, maybe it's unknown, maybe it's given, maybe you keep it as it is. But let me tell you something. If you have a vector equation like VB equal to VC plus VB with respect to C, this equation have an I component and have an J component. So from this equation, you can get two equations. You know the direction of VB. I know it's all in the I direction. So I know that VB has a magnitude VB in the I hat direction. Okay. And VC, I know that has a magnitude VC in the negative J hat direction. All goes down. All this informations, that's basics. You will not be giving this information in the problem because you will have to understand if this part has a vertical position, this point has nothing, has only one direction, this direction. This one, this direction. Either X and Y, and omega is this direction, so it has this. So all the magnitude are in the I hat direction. And VC, it's either going down or going up, so it's a negative J direction. But VBC has two directions. That's why I have to multiply these two. That's the key to solve this problem. I hope that you guys understand this very well. And sometimes I will give you in the problem like something maybe, for example, you have a bar like this, whatever the shapes are, and a bar like this, and something like this, but this not fixed. This is connected to something that has roller here, but can move in the X direction. So, and this is hinged. So you have to understand the same thing. Like if the omega is going this way, so I have, for example, A, B, C, and D. So I have VB is going this direction, and definitely VD has only one way to move in this direction. Before, I have VD is equal to 0. Here, I have VD has a value in the I hat direction. If I want to find out, I believe the omega of this body this way. So VC as an absolute going this way. But actually, this is VC with respect to D. This is not absolute. Absolute because VD up there was 0. So it was absolute. But right now, it's a VC with respect to D because right now, D is moving. I cannot relate C to a moving. We always relate to a fixed position. But if this position is not fixed, so I have to relate to it. So this is VC with respect to D. Right now, VC is equal to VD plus VC with respect to D. If VD is equal to 0, like the problem from before, so this is going to be 0. But right now, in the problem, maybe I give you the VD is equal to 4 meter per second. So right now, you have to put it here. And VC with respect to D is going to be the omega of this body. We said that it was omega before omega DC vector crossed by RDC vector. From before here, it's the same thing. VC is equal to the omega of this R multiplied by this R distance, which what we already have here, but VD was equal to 0. Right now, the case VD is not equal to 0. That's what you need to keep attention to. Like any example that you will be given, you will have to look at the boundary condition. Yeah, this point is fixed, so it's not gonna move. So VA is equal to 0. So VB is an absolute. But C right now in the other problem with respect to the fixed position D, right now D is not fixed. So right now I can say that VC is equal to VC with respect to D. Why? Because D is moving. So I have to add the other component, which is VD, right? So that's something that you need to take care of. Let's get back to the problem. I just try to explain what we have. Let me actually best it one more time here. Control V. All right, for this problem, right now C is moving, so I can say that VB is absolute with respect to C. However, B is absolute velocity with respect to A. Why? Because A is not moving. So if I'm gonna draw this problem again, I'm gonna make it like this, and this is not moving, and I have VC at angle 45 degrees. So I have VC is this way, and I know it. VB, if I wanted the absolute VB, and I know the omega, okay, I don't have omegas here. The velocity of the slider block is 4 feet up, inclined, determine the angular velocity. Okay, the angular velocities are not known for AP and PC. The velocity of point B at the instant is shown. Oh, and the velocity of point B. So it needs the velocity at point B. Okay. Before starting your computation, fully map the vectors below into a separate kinetic diagram. Okay, so it needs, all right. So right now I'm asking you to map the position vectors RP and RC with respect to B. If I want to do them, okay, let's do them. I have RP. RP is something like this. So this is RP, the absolute distance, because it's respect to O, or a point that is not moving. RC with respect to P. If I want to RC with respect to P, it's going to be something like this. RC with respect to P. So that's how it's look like. The absolute linear velocities. If I wanted the absolute linear velocities, RP, VB, and VC. Actually, VC is already mapped. This is the absolute velocity. VB, the absolute linear velocity. Okay, let me ask you, if I wanted the absolute linear velocity, show I relate it to A or I relate it to C? Can somebody answer this? So I don't feel that I'm talking to myself.
A.
You should
What?
relate it to A
A,
because
why?
it's the fixed one, and BA is gonna be zero. So
Exactly. Okay, continue with me. So if C is moving up, what is the direction of the omega? AB, is it gonna be clockwise or counterclockwise?
it should be clockwise.
All right, it should be this way, omega AB. How about BC, is gonna be clockwise or counterclockwise? BC. This part,
Counterclockwise.
Counterclockwise.
counterclockwise, omega BC. So I map the omegas, okay? So I know right now if I wanna find out VB with respect to A, so I'm gonna look at the direction of omega AB, so definitely VB is gonna go this way. So right now I mapped VB and VC is already mapped. So the next thing, the relative velocity VC with respect to B. All right, VC with respect to B. So if this is my arm, actually I have to make it perpendicular. So this is VC with respect to B. You will tell me, but there is no way that VC is gonna go up because it's restrained to move in 45 degree. That's right, but this is actually how VC with respect to B look like, because we are not looking at absolute velocity, we are looking at the relative velocity. At some point when this arm goes up, it's gonna be something like this. So it's gonna be here, like let's assume that this moved this way. This is the starting point, and C is moving this way, and actually no, it's not gonna be this one. This one is gonna be something like this, because once this is go up, this arm is gonna return this way. So right now this is absolute velocity, but this is the relative velocity to this point because it's always perpendicular. All right. Okay, so right now we mapped VC with respect to V. And right now I'm asking you to map the absolute angular velocity omega A and omega BC, and that's what we already did. So we did the mapping part. Let's do the practicing part. To practice mapping a bit more, create another kinetic diagram where VC, so I'm asking you another one that you make VC if VC is going down, not going up. So if VC is going down, let's do it here. VC is going down, what is going to happen? This is going to move this way, and this is going to move this way. It's going to be clockwise, and VB is going to be this way, and what else? It asks about, all right, if this, check. Okay, so it's the positions RB is not gonna change and RC with respect to B is not gonna change. The absolute linear velocity is changed in direction VB and VC. The relative velocity VC with respect to B, okay, I have BC and it's R moving this way. So this is gonna be going down. VC with respect to B is gonna go down. Why? Because the omega is going down this way. This is omega BC and this is omega AB. All right, so we did the mapping in the opposite direction. If we want to solve this problem, so can you imagine you only given one inputs, which is the velocity at C in this problem, and you are asked to get the two omegas and get everything in this problem. And I believe the key for this problem is VB. Like once you build the equation, VB is going to be solving the entire problem. But let's find out where's the instantaneous center of the velocity for BC first. Okay, so and right now, okay, this one, something like this. Moving up. Let me actually write it as a velocity. All right. So I have the absolute velocity VC is going up, and I have VB. It's this way. All right. So and I have this is the omega AB, and this one is going to be the omega BC. All right. If I'm going to write the equation of VB is going to be equal to VC plus the VB with respect to C. All these are vectors. So I write only one equation. And I expand this equation. I know that all VB are in the I direction. So I put VB in the I hat direction. VC, actually, I know where's the direction of VC. The magnitude is 4 meters per second, but I know the angle here is 45 degrees. That's what is given in the problem. If I go up, this is 45 degrees here. So I know the component in the X and the component in the Y. So if I want to know it, the VC is going to have 4 over root 2 in the I hat direction plus 4 over root 2 in the J hat direction, or 4 cosine 40 plus 4 sine 40 in the J hat direction. So I know where's the direction here. Omega VBC is omega BC. Just double check, it's the omegas. Yeah, because that was gonna make difference. Omega BC. See, some people have questions here. Some people ask 4 bars. Okay, we'll see about that. Omega BC cross by R. What we need VB. Let me see what I asked here. Okay, a relative velocity VC with respect to B. All right, so I have RB with respect to C. Actually, you can do the same. Actually, you can do this as VC is equal to VB plus VC with respect to B. You can do the same. It's just going to have some change in the directions. All right. I have these. Actually, I know RB with respect to C. I have this is point B. All right. I know that this is point B and this is R. This is point B and this is point C. And I know that this, I go RB with respect to C. So this is RB with respect to C. It's going in the negative I hat direction, and the value is 1 foot. So I know that this is -1 in the I hat direction. Sorry, this is omega BC that we need to put here. Omega BC, which I don't know. But actually I know the direction of omega BC.
How can you tell the direction? How can you tell the direction if it's gonna be positive or negative?
For the omegas or
Uh,
the R?
or they are.
Well, the universal direction are these. I, J, K. This is plane. So the plane is like, for example, this is gonna be I hat, this is gonna be J hat, this is the X, this is the Y, and this is the Z. All right. So if I'm giving you something like this, so I'm gonna assume it's a plane. My plane is IJ, and any something outside the plane is gonna be Z. And Z out of the plane is the positive. Inside is the negative. So I have R is going this way, so it's in the negative I hat direction. By the way, if you put your own directions, it's gonna give you the same thing. Like if you assume that this is different directions, it's gonna give you the same thing. But the universal, the convention, the rule is this is I, this is J, this is Z. Okay, so for this problem, we assume that, or not assumed, we based on the velocity
Oh.
direction.
Yeah, I'm sorry, because like on your BC, and so when you're doing omega BC and RBC, shouldn't we start from B then into C? And wouldn't that be positive I?
Okay, so if I have point B here and point C here, if I want to find B with respect to C, so this is RB with respect to C. We start with B and end with B with respect to, we start from C because we want to find out where's the location of B with respect to C. But if the opposite, I want to find out what is C, where is C with respect to B. So this is RC with respect to B.
Okay, thank you.
Right? Okay, so yeah, we have it here, RB with respect to C. I know the magnitude is 1 feet and it's in the negative I hat direction. So if you want to put them, I can put here -1 in the I hat direction. How about omega BC? Actually, we said that if C is going up and this is rotating this way, so this is gonna rotate this way. So that means that omega is counterclockwise and my finger is gonna go towards me. If it's counterclockwise, it's gonna give me positive K hat direction. So let's say it's gonna be omega BC in the positive K hat direction. Let's see how once we multiply, it's gonna give us negative omega BC actually. But let's see what direction. If you want to know the direction, you put I, J, K. If you multiply I cross J, it's going to give you positive K. K cross I is going to give you positive J. J cross K is going to give you positive I. Right now I have K multiplied by I. K multiplied by I is going to give you positive J. But we already have negative outside. So we are going to take the negative out. And this is going to be omega BC multiplied by 1. And it's going to be in the J hat direction. So right now, I know that VBC is equal to this. Why I'm getting this? Because I want to put it here. It's going to be omega BC in the J hat direction. So once, right now you have two equations and two unknowns. You have VB and you have omega BC and you have a vector equation in the I and J hat direction. So what you are going to do, you are going to separate the variables that are in the direction of I hat and separate the variables that are in the direction of the J hat. So you make I hat and put what are the variables that are in this direction. So you'll find that you have VB and you find that you have this 4/√2. So you got this one. And then J hat, you don't have something on the left-hand side. So you have 0. On the right-hand side, you have 4/√2. And also you have negative omega BC in the J hat. Then you can find VB and you can find omega BC. That's how you solve any problem. You start by the relative equation, okay? So some of you ask about 4 bars. I believe this is gonna be huge problem. I mean, but we can do it with 3 bars like that we did before. Like if it's something, not sure. I didn't see one that has 4 bars before, but let's. I did this before, like this one, but let's see. Definitely, I will have to give you lots of information about problem like this. If I told you that this is moving this way, so if this is moving this way, this omega of this body is gonna move this way, and this omega of this body is gonna move this way, and this is gonna move this way because this whole structure is gonna fold down. Okay. All right. If we want to map the velocities, so let's say that this is A, B, C, D, E. So VB is gonna be this way. VD is gonna be this way. VC can be calculated from the right side. So if you want a VC with respect to D, so it's gonna be something VC with respect to D. But if you want to calculate it from from the B side, so it's gonna be something VC with respect to B. It's gonna be something like this. All right. So usually the absolute velocities are related to the instantaneous zero velocity. So right now, I have this point is fixed. So this is instantaneous center of zero velocity. This point is fixed. So this is instantaneous center of zero velocity. And the good thing about the instantaneous center of zero velocity that has a velocity equal to 0, and you can get VB with respect to A is the same as VB. So you directly VB is going to be equal to the omega of AB multiplied by RB with respect to A. But actually, let's put the R versed so that actually, no, the omega is versed. I always get confused with that. All right. So I always put it this way. Why this is simple? Because I don't have to put RA before. But if A is moving, this is going to be different. If A is moving, I'm going to say that VB is going to equal to VA plus the omega AB crossed by RB with respect to A. If A is moving. If A is not moving, so VA is going to be 0, and I always have this equation. Okay, I hope that you guys understand this. But what I'm going to do, like for this problem, I'm going to give you only one variable. Maybe I give you the omega of this line. Like I'll give you, for example, this omega. If this omega is known and I give you this R distance, you can get VB. And once you get VB, it's going to be easy for you to get VC because VC is equal to VB plus the omega multiplied by this RV, and then you can calculate the VC. And if and then you start from here and go all the way down until you come here. How can I do this? By substituting in this equation. Like I give you this omega, you already have the omega, you already have the R, you can get VB. Once you know this, you use this R to get the velocity at VC. So you will say that the velocity VC is equal to VB, which has already calculated, plus the omega BC crossed by RC with respect to P. Solving this equation is going to get you VC, the V at C, and it's going to be the absolute velocity at C. Here you have VC is equal to VB plus VC with respect to B. Okay, so right now we mapped the VC with respect to B, but how can we map the absolute velocity at C? Okay, let's actually. let's do it. For this one, actually, it's much easier. Let me control V this. Right. So right now, we know that okay. So right now, do you guys remember how to get the instantaneous center of zero velocity for anybody? So what I have to do, I need to get, for example, the absolute velocity here. This is VB, and this is VC. And once I know the direction of two velocities, we draw perpendiculars. And I draw perpendicular here. So this is the direction, let's say it's moving up. So this is the direction of the omega. This is the instantaneous center of zero velocity of these two bodies. So if you want to calculate VB, this one, you multiply omega BC by this R. I can actually do this. Right now, for example, actually, this is another solution for the problem, and I believe I did it in the notes. So also you can look at that. Try to identify where is the instantaneous center of each bar. This one was easy. Why? Because A was fixed. So I know that this is the instantaneous center of this one. Okay, so right now I know VC is equal to 4 feet per second, and I know that this is 1 feet and this angle is 45 degrees. So this angle also is 45 degrees. So this is 1 feet, and this is going to be 1 root 2 from the Pythagorean theory. So I already know the arm. So if I want to find the omega BC, I know that the omega BC multiplied by, let's say that this point is I, is going to be this omega multiplied by RC with respect to the I is going to be equal to VC. I know VC already 4 feet per second. I know RC with respect to I is already 1 over root 2. So I can get omega BC, which is VC, which is 4 feet per second squared, and divided by RC, which is 1 over root 2. So it's going to be 4 over root 2. And that's actually the same solution that we got from before. If you go up a little bit, once we solve it, okay, here we go. It's freezing. Just okay. Yeah, if we go up a little bit, here, yeah, do you guys remember? The omega BC is 4 over root 2. That was actually much way simpler solution to this problem. So I try to find out where's the instantaneous center of zero velocity of this bar. So how I know this direction and I know this direction. This is where these points are moving. So I make perpendicular to these two, and this is how I get the instantaneous center of zero velocity. If you guys revise the notes, you will find there's many ways to identify the location of the instantaneous center of zero velocities. So if you know 2 points, like for example, I know a velocity of this and the velocity of 2 points on this body, or the direction of these two velocity, I make a perpendicular to this velocity, and this is the instantaneous center of zero velocity. I know this body is moving this way. And if I want to know the omega of this body, if I know the VP and I know this R, the omega is going to equal V over R. Why? Because V is equal to omega crossed by R vector. I can do this for any problem. Same thing with the 3-bar linkages. It's just freezing. Just give it a moment. Okay, yeah, so let's say that we have, do you guys understand this? Does anybody have any specific questions on this? All right, so if I have 3 bars, something like this, and I have, this is fixed here, and this is fixed here. And I think it's becomes heavy. All right, so I know that this is an instantaneous center of zero velocity. And this is an instantaneous center of zero velocity for this bar. And if I'm saying this is moving this way, so this is gonna be the direction. So, and this, and actually this is gonna move this way. So VC is gonna be this way. So if I wanna, I know these two bars, AB and DC, but this bar BC has a general plane motion. I can't know where's the instantaneous center of zero velocity, but I can draw a perpendicular to this bar and perpendicular to this velocity, and the instantaneous zero velocity of this bar is gonna be here. And I don't have to multiply any vectors. Once I did some geometry and I identified these R's, knowing the velocity at C or the velocity at B is gonna allow me to get what is the omega for this bar. Same thing with, let's draw this 4-bar again. If you have something like this, and let's say it's 4 bars, and these 4 bars are fixed here, and I told you that this bar is moving this way. So definitely this bar is moving this way, and this bar is moving this way, and this bar is moving this way. So this velocity is like this, and this velocity is like this. In this one, if I'm looking at this part from the right side, here's the direction of the velocity of this point with respect to this point. And if I'm looking at this part from this way, this is the velocity. All these are absolute velocities. Not absolute, this is actually relative velocities. So it's gonna be, okay, so here, we will have to know if this body is moving, this point is moving where, so that we can identify the, right now I can know what is the absolute, we cannot know the absolute velocity of this point. So that right now we have to solve it with the relative velocities for this one. Because I know the absolute velocity of this one, but this one we can't. Like, for example, I can give it to you like this point is moving at a specific location. So based on this, like if I told you that this point is, if I restrain it for you, all right. Like if I told you that this point is moving this way down, so you'll have to draw a perpendicular to this velocity and a perpendicular to this velocity, and you identify the point, the instantaneous center of zero velocity. For example, another example that is practical, like I give you something like this and something like this, and here something like this, and I told you this point is moving this way. Right now I'm restraining this to move this way, okay? And this one is moving this way. So right now you'll have to find this by the relative velocity, this with respect to that. So you cannot do it with the instantaneous center of zero velocity. So instantaneous zero velocity, you have to have a member, and you know where are the absolute velocities at the point at the start and the end. And let me tell you an application to this, and let me look at the notes because I believe I have it somewhere in the notes. Yes. Is center of the velocity. Yeah, this one. Take this one. Look at this example. This is a direct application on the instantaneous center of zero velocity. So there's some applications that has an instantaneous zero velocity, like when you're driving your car or your bicycle, it's moving on the ground, so the ground is not moving. So we consider this instantly an instantaneous center of zero velocity. And all the points, like if you wanna, and we say that this is moving, not about this point, because this point is moving this way, it's free. Okay, how? Because this wheel is moving with an omega about this point, and if you wanted to find the velocity at any point on the wheel, you will have to multiply the omega by r, and r is measured from the instantaneous center of the velocity here. So this is v. And v is linearly increasing as you go away from the ICZV, the instantaneous center of the velocity. So if this is v, this is going to be half v. And here is going to be something like this. Is like this in one of the at any one of these points. You multiply the omega by the r with respect to the instantaneous center of the velocity. Same thing with pulleys. For pulleys, you have something like this. This is the cord, and you have your pulley here. So this is an instantaneous center of the velocity. And if you know the velocity here, which is 0, and you know the omega, how this pulley is rotating, so you can know what is the velocity at this point. So you can know if it's rotating this way, so it's going to be something this way. And this is a direct application here. All right. Okay, so look at this problem. I give you a system of pulleys, and I told you only one piece of information. I told you that point F is moving with 0.5 feet per second. All right, so you will tell me, where can I find the instantaneous center of zero velocity? Okay, I have two cords here, one this way until here. This is one, and the second one is here. This one going all the way until it comes here. These two. Okay, let's delete them. All right, so I know this is fixed from the top here and goes all the way down. So this an instantaneous center of zero velocity. So I know that the velocity at this point instantly is equal to 0. And I know what I'm asking for. I'm asking for the velocity VA. I want to know VA is going up and down and how much. But definitely, if I know that F is moving down this way, so all this cord is going to go up. So this pulley is going to go up, and all this pulley VA is going to go up. So I know that VA is going to go up, but I don't know what is the value of VA. But I know VA is function in the distance from here. So as soon as I go away, the velocity on this pulley is going to go up. I mean, like, it's going to be much more. So if this is VA, VA is going to be equal to the omega multiplied by R. If I know the omega of this pulley and I know this R, I can get it. How about the velocity at B at this point? The velocity as B is the same omega multiplied by 2R, because this one and this one. So definitely VB is equal to 2VA. So it's gonna be something like this. And since I know the velocity here, 2A, I can know the velocity here because the velocity on all this line is the same. So this is gonna be also 2VA. And I know as well, like this ball is moving, but I don't know where is the instantaneous center of zero velocity. It's somewhere on the pulley, somewhere here. Like if I know the velocity of this one is rotating, is gonna be rotate this way. So I know that this one is gonna go down. But if you wanna know the velocity, you keep track them, you keep track the chord. Don't leave the chord, keep going with the chord. Let me delete these, okay? Okay, so right now, let's subtract this chord. I know that this is 0 because it's fixed. This is going all the way down until it comes here. So the velocity here is 0. And I know that the velocity here is VA, and this is an instantaneous center of zero velocity, so VA is going up. And once I know the V here, I can know the omega because I know R and I know A, so I can get the omega. Once I knew the omega, I can multiply omega by 2R, so I can get the velocity at the end here. So I can keep tracking of the chord until I come here, and I knew that the velocity of the chord here is 2VA. And it's gonna be 2VA until it goes up. So here is gonna be 2VA as well. And I keep going with the chord, it's gonna be 2A. And here at this pulley is gonna be 2A here and 2A here because it's gonna go down. And this is an instantaneous center of zero velocity. So why? Because this is fixed axis rotation. This pulley is gonna move this way. And if I know the omega of this pulley, it's gonna be the omega multiplied by R. And here's the omega multiplied by R, but it's in different direction. So I have 2A's going up and 2A's going down. Let's go down. This is gonna be 2A. So right now I know 2 points here. This is 2A and this is 2A. If I wanna know the instantaneous center of zero velocity, you will have to draw a perpendicular. If you draw a perpendicular here and here, so you will find it's something in between them. And since they are equal, so it's in the middle. This is 2A and this is 2A. So this is the instantaneous center of zero velocity. And if you want to keep tracking of the velocity, you can draw an extension line, has the value here and the value here. And then you will find that the velocity at this point is equal to 6VA. How? You know that, let me get it out there here. If I have this body, and I told you that you have a point here, and a point here, and a point here. And I told you that the velocity here is 2 meters per second, and the velocity here is 2 meters per second. I told you before, if you want to know the instantaneous center of zero velocity of a body, you draw a perpendicular on this body and a perpendicular on this body. They are going to meet each other here. So the instantaneous center of zero velocity is somewhere in between these two velocities. If this is 6 meters per second, the instantaneous center of zero velocity is going to be closer to this velocity. But if this is bigger, it's going to be closer. But if they are equal, it's going to be in the middle between them. So I knew that this is an instantaneous center of zero velocity. So if you know this, you can get the velocity at any point on this body. So you can get the velocity here. So knowing the distance, I know here we have an example of a circle. You know the center has 2 VA and here has 2 VA. So I know that the instantaneous center of zero velocity is between these two, is something in the middle here. So if I want to know omega, so omega is going to be equal to V over R. R is not the radius, R is the distance between these two. So V is equal to 2 and R is half the radius, half R. So right now I know that omega is equal to 4 the radius. So if you want to know the velocity here, so you are going to multiply V, is going to be omega multiplied by the distance. So the distance here is 1.5 the radius, because I have this is radius and this is 1.5. So I have omega is 4 the radius multiplied by 3 over 2 the radius. So when you do this, it's gonna be 2, and this is 2, it's gonna give you 6r. So the velocity is 6 times. That's why I put here 6 VA. How? I identified the center of the velocity. And actually, you can do some geometry. Like if you know that this is 2A and this is 2A, so the velocity is linearly, because if you have somebody's moving and you know that this is an instantaneous center of the velocity, so you know if this is V, if you want to get in the middle, it's going to be half V. If you want to get in the quarter, it's going to be 1/4V, and keep going down until it becomes 0. Okay, so this is going to be V6A. So I go all the way up. V6A is going to be V6A here and V6A here. So the velocity of the body F is equal to 6VA. So 6VA, if I have the velocity here, 1 meter per second, the velocity of F is going to be 6 meters per second. But right now, this case, I know the velocity at F is equal to 0.5 feet per second. So 6 VA is equal to 0.5 feet per second. So if you want to get VA, so it's going to be equal to 0.5/6. So I believe this is one of the most interesting applications on the pulleys with the concept of an instantaneous center of zero velocity. You can solve the same problem using the chapter 1, the relative motion. You get the length of the cord and you know that the velocities, and you differentiate it. You are gonna sum this distance with this distance and you try to find the datum. It's gonna give you the same thing. But what we did here, we solved this by the concept of the instantaneous center of zero velocity. So I'm just gonna give you one last comment on this problem. All what you want to do is to find the instantaneous center of zero velocity of all these pulleys. And just focus, you have this rope here, and this point, the rope has 0 movement. It's here is 0 because it's fixed here. At this instant it's 0. So this is the instantaneous center of this pulley. Because this pulley is the same like something is moving on the ground. So this is an instantaneous center. However, because this part is not moving and this part is moving, like this one is the moving part. So that's the one that is moving. So this one is not moving right now at this instant. However, for this pulley, I have this one is moving and this one is moving. Both of them are moving, but they are related to these 2 pulleys. These 2 pulleys are fixed axis rotation here. Okay, so knowing the velocity at the end and the velocity in the middle, I was able to know where is the instantaneous center of the velocity. And I can relate of that. So can you imagine with only knowing one velocity, which is this one, I can know the velocities of all these bodies, how they are moving. Okay, I hope that this is not complicated, but I just like wanted to show you the different ways for the instantaneous center of the velocity. I hope that this is enough for you guys. It has been 12:30, so just let me know if you guys have any few questions in the last 2 minutes so I can explain them. You can start your review. If you have any questions, any urgent question, send me on Canvas and I'll try to respond to you as soon as I get to my computer. Right, so I'm happy to take any further questions if you guys have. Definitely try to press on the instantaneous center of the velocity. Try to know how to do it, where it is, and what is the concept of relative velocity, because this is chapter 16 and 17. We haven't been tested in them, so we need to be like confirmed about our knowledge about them. Does anybody have any other questions?
Can I talk to you after like the Zoom meeting's over by chance?
Absolutely. All right, so if you guys don't have any questions, I guess I would meet you guys on Thursday at 9:30 in the classroom that we have the exam at, which I believe EC, I don't remember, but you guys know where it is. So you guys see you there, just do your best, try to have a plan. It's just 2 days, just go through the chapters and do your best, and I believe you guys will do great, don't worry. All right, so
Thank you, Professor.
thank you.
Professor.
Thank you, Professor.
All right, have a great day, guys. Hi, Sebastian.
Hi, sir. I was just wondering, I just want to ask you really fast, for the exam,
Hmm.
the exam is, it's gonna be, is 6 questions or 5 questions?
5 questions.
5 questions, okay, and it's gonna be 2 of 16, 17, and 3 from everything else you learned before, correct?
Yes.
Except fluid.
Yes.
Okay, and also one more thing, for the, for my extended time, can I come, do I like arrive to your office around?
8:30? 8:30
Um,
or after?
I was gonna say like around like 8:15, like just be safe on the safe side.
Well, I believe, okay,
Is it 8:30 or 8:15?
because you only get 0.5x, right?
Yeah,
So it's gonna be from 9:30 to 11:30, so you get 1 hour more, which is 8:30.
okay, yeah. So I arrived to your office?
Yeah.
All right, office on your 3rd floor, correct?
Hmm?
3rd floor of EC?
Yeah, the one that you come to it.
Alright.
But one thing, when we walk to the exam room, you will have the exam closed in your notebook or whatever. You will not and you will not open it until we start the exam in the room. So this is gonna give, like, maybe you will lose 5 minutes. Maybe I can let you start the exam 5 minutes early.
Okay.
Okay, until like everyone is settled and get his exam, and then you start from where you stopped. Okay.
Okay, yeah,
All right. Perfect.
you're perfect. All right. Thank you, sir. See you
I'm sorry.
8:30 Thursday.
Perfect. Okay. Thank you. Have a good
Thank
day.
you.
Bye.
Good day.